Welcome to this video on the Zeeman effect, named after Dutch physicist Peter Zeeman, who discovered it in 1896. In 1896, Zeeman was studying sodium spectral lines in a flame placed in a strong magnetic field. He expected a simple line shift, but what he found was a direct connection to quantum mechanics, revealing angular momentum quantization and selection rules. The Zeeman effect is the splitting of atomic energy levels under an external magnetic field. This happens due to the interaction between the magnetic field and the magnetic moment of electrons, causing a distortion in their energy states and spectral line splitting. There are two main types of Zeeman effects. The normal Zeeman effect involves splitting due to the external magnetic field and the orbital magnetic moment. The anomalous Zeeman effect is caused by the interaction with the combined orbital and intrinsic magnetic moment. For a single electron, the perturbation to the Hamiltonian is shown here. The splitting nature depends on whether the external field is much weaker or much stronger than the internal spin-orbit coupling field. In the weak field Zeeman effect, the Zeeman correction to the energy in first-order perturbation theory is defined using the Landé G factor, Gj, where the electron spin has been set to s equals 1/2. The Zeeman energy correction is expressed with the Bohr magneton, μb. The total energy is the sum of the fine structure part and the Zeeman contribution. Before moving on, let's briefly pause to talk about the polarization of the emitted light. The polarization tells us which type of transition has occurred. Sigma polarized light is circular and appears when the change in the magnetic quantum number, delta m sub j, is plus or minus 1. Pi polarized light, on the other hand, is linearly polarized and occurs when delta m sub j is 0. Consider the n equals 2 states under weak field Zeeman splitting. Because the external magnetic field is weak, the spin-orbit interaction remains dominant, and the good quantum numbers are n, l, j, and m sub j. The unperturbed energy of each state is given by the fine structure energy, which depends only on the total angular momentum j. Using the formulas introduced earlier, the effect of the magnetic field is treated as a small perturbation, leading to a first-order energy correction that depends on the Landé G factor, the external magnetic field, and the magnetic quantum number m sub j. This term represents the expectation value of the Zeeman interaction evaluated in the unperturbed states. Therefore, the total energy of each state is obtained by adding this first-order correction to the fine structure energy. This diagram illustrates how the energies of the n equals 2 states evolve as the external magnetic field increases, demonstrating the weak field splitting. In the strong field Zeeman effect, the external magnetic field is strong enough that the Zeeman interaction dominates over the spin-orbit coupling. As a result, the good quantum numbers are n, ml, and ms. The Zeeman interaction is given in first equation. In this regime, we include the Zeeman term directly in the unperturbed Hamiltonian. The corresponding energy levels, neglecting fine structure effects, are shown in second equation. Since the fine structure is now a small correction, we treat it using first-order perturbation theory. The resulting energy correction is given by third equation. Here, the operators h sub r and h sub so are the relativistic and spin-orbit fine structure terms, respectively. Combining the energy expressions for relativistic and spin-orbit corrections, we obtain the first-order fine structure energy correction. The total energy is the sum of the Zeeman part and the fine structure contribution. In this strong field regime, the Zeeman effect is also known as the Paschen-Bach effect. The intermediate field Zeeman effect is where neither the external nor the internal field dominates. The total perturbation is the sum of the Zeeman and fine structure Hamiltonians. We use degenerate perturbation theory, starting with the LS coupled basis set. The perturbation matrix, or W matrix, is constructed to find the energy eigenvalues. The characteristic equation for the first 2x2 block is shown here. Solving the characteristic equations for both 2x2 blocks yields these completely general solutions, which apply across all values of the magnetic field strength. The Zeeman effect has practical applications, including measuring magnetic fields. It's also utilized to improve accuracy in atomic absorption spectroscopy and is relevant in various resonance spectroscopies and magnetic resonance imaging. Here are some visual examples of the Zeeman effect in different contexts, such as solar observation and plasma diagnostics, illustrating how spectral line splitting indicates magnetic field strength.